In this video, I will explain you Lcr series circuit. Now, as the name suggests, we have L, that is inductor, we have C, that is capacitor, and we have R, resistance, connected in a circuit. And how it is connected? It is connected in series. So I will draw the circuit here. I have a resistance, and I have an inductor, and I have a capacitor. So order doesn't make any difference. You can take it as LCR or you can take it this way. It's the same thing. Okay. And AC is connected across the circuit. Now, you know one important thing. When elements are connected in series, it's the same current that is passing through all the element. Magnitude will be same and the direction would be the same. So the first thing you have to mark is I. This is Im sin omega t. Okay, whatever it is, we will first derive the equation and we will see whether it is Im sin omega t plus phi or minus phi, or is there any phase difference. We will see after the derivation. Okay. Now, when elements are connected in series, the potential across each element won't be the same. Here it would be one value, here it would be next value, here it would be next value. But to get the total potential difference, we have to add VR to, VR is nothing but potential drop across resistor, and we have to add VL with this, and we have to add VC with this to get the net potential difference in between these 2 points. So potential difference in between this plus this would be this. Okay. Now we can't add it like numbers. For example, if it is 2, if this is 3, if this is 4, we can't add 2 plus 3 plus 4 to get the final value, because these, we don't know whether these are in phase or out of phase. See, if everything in the same phase, then I can add all these values. Okay. This means that, let's say here voltage, when at resistance the voltage is 2 volt, and if it is in this direction. Now here if the voltage is in this direction at that time, and here the voltage is in this direction, then we can't add these three together as 2 plus 3 plus 4 to get the net value, because these two are in the opposite direction. So we have to subtract and do, it's not a vector addition, these are out of phase, so we have to make it in the same consideration or in the same way, then only we can add it. Okay, so don't get confused that these potential difference are vectors. These are scalars, but we can't add like numbers because they are not in phase. If they are in phase, then we can add these numbers. Okay. Now we will see what is the potential across each element. In current, in resistance, we know that the potential would be in the same direction. Because we have learned it that they are in phase. In inductor, current lags voltage, so voltage here would be leading. And this is current is lagging voltage by 90 degree. In capacitor, current leads voltage. Okay. In capacitor, current leads voltage by 90 degree. This is voltage, EMF. This is EMF and this is EMF here. Now this is EMF across resistance. This is EMF across inductor. This is EMF across capacitor. Now we are considering counterclockwise rotation here. Okay. So here the phasor of EMF is forward by 90 degree with respect to current. Now here current is forward 90 degree with respect to EMF. Now I will give you a small trick to memorize. In current lags in inductor and current leads in capacitor. Now I am only going to mention about current, whether current lags or current lead. In inductor is represented by L, right? L means lags. So current lags. Okay. Now capacitor is represented as C. So C gives more priority to current because current starts with letter C, current. So in capacitor, current leads. Current is having C as the first letter, so capacitor, current is the priority that leads. Now in inductor, it is represented by L. L stands for lags, so current lags. We are only speaking about current here. Okay, so there is no confusion. Okay, now we will put everything in one equation. So first I will represent the phasor diagram. Now first I will consider current because that is the common thing here. So this is my current I. Okay, Im sin omega t plus phi or minus phi, whatever it is. Okay, now we know that in resistance voltage will also be in the same direction. Potential difference across resistance would be in the same direction as that of current. Direction means both will be in phase. The phasor would be in the same direction. See, this direction doesn't mean that it is vector. Both are in phase. So voltage would be in the same direction. This would be voltage. So the whole thing is the voltage. And this is my current. Both are in phase. And this is E is equal to Em sin omega t. So this I can immediately represent it as Em sin omega t because that is my input. E is equal to Em sin omega t. And for current I can't mention it as Im sin omega t because I don't know whether that is in phase or out of phase or what is the net phase difference. Okay. Now this is VR, potential drop across resistance, and current is the same across all the elements. So for current I only have to draw it once. Now comes inductor. In inductor voltage lead. So this is VL. VL or EL both are the same. Okay. Now in capacitor this is the current and current lags. VC. Now see, sometimes VL can be more, sometimes VC can be more because VL and VC are connected with XL and XC. Okay, so here in this example I am going to consider VL is greater than VC. Now in NCERT it is given that VC is greater than VL. It is the same thing. Okay, same thing means, see, derivation and everything, equation and everything would be the same. Only the difference is when VL is greater than VC, that will be, this circuit will be more towards inductive nature. Okay. And when VC is greater than VL, that will have more capacitive nature. That is the only difference. Okay, that is the only difference. Either you learn as given in NCERT where VC is greater than VL, or as per my equation, both are the same. Now in the picture VL is greater than VC, so I am going to consider in this way. Okay, now VL and VC are 180 degree out of phase. So I am going to take the net here. So I am going to take VC here. This will be VL minus VC. Now after deducting VC from VL, from the whole thing I am deducting VC. So this will be like this. So in your exam, all the pictures should be there. I don't have enough space here. So I have, from the whole thing, I have deducted this much. So from VL, I have deducted VC. So that is not there. Even VL is also not there. This is VL minus VC. Now, how to get the total potential difference? I have to add all these three, right? So I have already added VL and VC. Now I have to add VL minus VC and VR. So they are 90 degree in between, right? So if the vectors, it's not vectors, if the directions are 90 degree in between, then how to get the net root of VL minus VC the whole square plus VR square, because this is VR and this is VL minus VC and that two are making 90 degree. So if this is 3 and if this is 4, then its resultant is root of 3 square plus 4 square, that is 5, right? So in that way I could say that the net EMF is equal to this thing. Now net EMF or net voltage, both are the same. So I have mentioned V here, so I will mention it as V here. And we know one more thing, these are maximum values, right? Maximum value, this is VL minus VC is the maximum value and VR is the maximum value, okay? And its X projection will be, this would be EM sin omega t here, okay? So anyway, this is my maximum value and this one is VL minus VC is my maximum value. Here VL initially I have given the maximum value and VC I have given the maximum value. To get the instantaneous value I have to do the projection here, okay? Now I also know that V is equal to IR. Now VR is equal to I into resistance and VC is equal to I into XC, this is capacitive reactance, and VL is equal to I into XL, where XC is equal to 1 by C omega and XL is equal to L omega. And I know these equations. See, now, see, these are proportional, right? See, if I is 2, now this is 2R, VC is equal to 2XC and VL is equal to 2XL. Now if I am drawing a vector in this way, my VL minus VC, VL is nothing but I into XL, VC is nothing but I into XC. Now this is I into XR, sorry, XR, not XR, resistance. Now here I into, take the common term, XC, XL minus XC it is. So both are a constant multiplied by values. So if you are removing the constant, it would be in the same direction, but the size would be little bit different. For example, if this is 6, 8 and 10, on dividing all the number by a constant of 2, then the triangle would be in the same way, only the difference is angle and everything would be the same, these angles, but the difference is this will become 3, this will become 4, this will become 5. So my point here is, as these are VL minus VC is nothing but I into XL minus I into XC, so that is I into XL minus XC, here in this case I into R. So just on removing I from both of this, we will get a new value, that is XL minus XC here and XR here, and its resultant would be this, and that would be root of XC minus XL the whole square plus XR the whole square, and that is the net resistance of this circuit. I can't call it as resistance, net reactance, okay, because XC and XL are reactants, inductive, capacitive and inductive reactants, and this is XR. Instead of R I have to mention resistance of the resistor, okay. Now this is nothing but impedance. So Z is equal to root of, this can be XC minus XL or XL minus XC. Here my XL, VL is greater than VC, so I am going to take it as XX L minus XC the whole square plus R square. Now see, if at all XC is greater than XL, the equation will be XC minus XL. But see, this would be 2 minus 3 the whole square or 3 minus 2 the whole square. It both would be the same. 2 minus 3 is minus 1 square 1. 3 minus 2 1 square 1. So either it is positive or negative, it would be the same. So I am saying, if you are taking XC VC as greater than VL, you would be able to get the same impedance. So what is the impedance? This. And what does impedance represent? That is the net opposition offered by an Lcr circuit. Okay. Now I'll remove all of this. Okay. Now net impedance is equal to root of XL minus XC the whole square plus R square. Now these are my, this is XC minus XL, XL minus XC as per my picture, and this is XR, not XR, R. And the resultant here is of these two is parallelogram law of vector addition. This is the resultant, and that is the impedance Z, and the value of Z is root of XC minus XL the whole square plus R square. Okay, so that would be in this direction, complete the parallelogram, and this is the resultant. This is R, sorry, Z, and the value of Z is root of XC minus XL, root of XC minus XL the whole square plus R square. Now this would be, now I got the resultant, right? This is the resultant of VL minus VC and VR, and that is in this direction. Then that is the net potential difference across this. So this is my potential now, EM. E, this is EM. Okay, now here I can say that, see, if I am considering this as omega t, that is with respect to x, my net potential makes an angle of omega t, then this one, my current is nothing but, you know, 5 difference, 5 angle less than omega t. I would repeat it again. See, now I got VL minus VC in this direction. Now this is potential across R, VR, this one is VL minus VC, and the resultant of these two is the net potential difference, right? The total potential difference, that is VL minus VC the whole square plus VR the whole square and square root of this. And I already got the value of current, that is in this direction along VR itself. Now see, the net potential is making an angle of 5, it's not 90, it's less than 90, so the angle is 5 with respect to VR. So always we will take omega t as the angle that potential makes with our x-axis. So if I am taking this as omega t, now from omega t, phi have to come down to get our current. Okay, so I am going to mention E as EM sin omega t, but our current I is equal to phi less, that IM sin omega t minus phi. So here in this case, you know, current lags EMF by an angle of phi. So current lags is nothing but a property of inductor. So that is what I have told you. See, when VL is more than VC, now it will be more inductive in nature. What is the proof here? Here current is lagging, but that is not pure inductive. If it is pure inductive, current lags by 90 degree, but this is current lagging by an angle of phi. So this is an inductive circuit. Effectively it's an inductive circuit, but this is not a pure inductive circuit. Now how to get the value of EM and IM? So we know that EM divided by R would be IM. Now instead of R here I have, you know, the combination of LCR and the effective reactance I have to mention here. So that would be Z. And what is the value of Z? Z is equal to root of XL minus XC the whole square plus R square. Now if you ask me how to get the value of phi, this is the angle phi. So from here I can easily get the value of phi from, this is the triangle, this one is the right angle, right? So I can take cos phi or I can take tan phi. So cos phi is adjacent by hypotenuse, R by Z would be cos phi, or I can take tan phi. If Z is not given in the question, mostly it won't be given, but cos phi is required here. I mean that is required for power factor. So anyway, here I will take tan phi. Tan is nothing but opposite by adjacent. So opposite is this one. XC minus XL. Okay, this is opposite. XC minus XL. So XL here in this case XL minus XC. So XL minus XC. See, this would be the same side. Okay, this would be the same side. XL minus XC divided by adjacent R. This is tan phi. So phi is equal to tan inverse of XL minus XC divided by R. So this can be XC minus XL as well. So but in that circuit, current would be leading. Okay, in that circuit, current would be here and voltage would be here if you are taking VC greater than VL. Okay, now this is the Z value and I have given the value of phi, that is tan inverse XL minus XC divided by R. Okay, and one more thing, this triangle is very important. I will redraw it here. Very important. Okay, how did I got the value? This one was my XL minus XC and this one was my R, and I have drawn this, and this is the resultant Z, and this I am just mapping it here. This is XC minus XL and this angle is phi. See, this is the triangle. This one is Z, this one is XC minus XL or XL minus XC, and this is R, this is phi. Now from here you can find sin phi or cos phi or tan phi, whatever you want, you can get it from here. So this is very, very important. Watch the video twice or thrice till you get a proper idea. Okay, so impedance, concept about impedance is very important. The value is root of XC minus XL the whole square plus R square, that is the impedance. And maximum value of EMF divided by impedance will be the maximum value of current. Next important things, and here if VL is greater than VC, then I could say that this is more inductive in nature, and in that case more inductive, right? So current would be lagging voltage by an angle of phi, and the value of phi is tan inverse XL minus XC divided by R. Now if capacitive voltage drop across capacitor, if it is more than voltage drop across inductor, then we will get this one as VC minus VL. So this equation would be same because XC minus XL or XL minus XC the whole square is the same, but here phi will be just the opposite, XC minus XL divided by R. In that case, our net voltage will come here, and now that voltage would be lagging the net current. Okay, so in that case current is leading, so that is more capacitive in nature. Okay, thank you.